Hello friends, in this session we are going to see two very important topics for UPSC exams, be it CSAT, CAPF or EPFO. The topics names are number system and unit digit accuracy. First we'll start with the number system. Under the number system we are going to first see how the numbers are bifurcated under different types, that is the number tree, and then we'll see different types of the numbers and some examples based on those categories. For example, rational number, irrational number, composite number, prime number, square number, non-square numbers, and what are their different identities and the type of the questions. So let's start with the very basic, that is the number tree. So when we say number tree, we start with the very basic or most general form of the number, which we call a plus ib. A plus ib is called the general form of any number because it has two parts. One part is called as the real, another part is called as the imaginary part because it has I into it. I means iota, its value is under root of -1. So this part, as I said, is called real. This part is we called imaginary, and the combination of which is called as the complete number. So what do you mean by a real number? Real part of it. Real number is the number which can be shown on number line. So any number that can be shown on number line is called as the real number. So I hope you know what the meaning of number line is. Number line is the representation of numbers on a line where in the center there is 0. On the right hand side there are positive numbers like 1, 2, 3 up to infinity. And on the left hand side there are negative numbers like -1, -2, -3 up to minus infinity. So if I ask you, can you show a number 2 on this number line? So yes, definitely there lies the 2. Can we show a number 2.5 here on the number line? So yes, 2.5 will be exact in the center of 2 and 3. So this is how you can show the 2.5. If I ask you, can you show 2.33 on this number line? 2.33 means 2.33333. So yes, we can show because 0.33 means basically 1/3. So it is 2 complete and 1/3. So 2 complete, that means this much complete. And then the remaining part, if we divide into 3 equal parts, we want 1 part out of that 3 parts. So this is the point which shows 2.333. If I ask you, can you show 2/3? So 2/3 means you have to take 3 parts of the unit distance from 0 to 1, and we have to select 2 parts out. So if you divide it into 3 equal parts, we have to select 2 parts out of it, out of 3. That means this is the point which is 2/3. So we can show all such numbers which are integers, decimals, the decimals which are never ending, the decimals which is in 2/3 form. What about the surds? If I ask you, show √2 on this number line. Can you show √2 as a distance on this number line? Not approximately, accurately. Yes, we can show √2 also on the number line because if you count this distance is 1 unit. So if you take 1 unit distance and if you draw same distance as perpendicular, so both are 1 unit. And then if you draw the hypotenuse like this, you know this distance is 1 unit. This distance will also be 1 unit. And using the Pythagoras theorem, the hypotenuse is going to be under √2. So you can measure this distance now in your compass, keep the center at 0, and then mark wherever it is passed from is the distance that is √2. It is approximately 1.4 something. So it passes up between 1 and 2. And that point is √2 on the number line. So this is how you can denote √2 on this number line. That means on a number line, you can show a number which are positive numbers, which are negative number. Negative numbers also can be shown. For example, -3. Then you can show decimals. You can show decimals which are never ending. You can show fraction. You can show surd. So all such numbers, because they can be shown on number lines, are called as the real numbers. So whatever number which can't be shown on a number line, they are called as the imaginary numbers. So you can't show under root of -1 on number line. Hence that is called as the imaginary numbers. Now, imaginary numbers won't be part of any exam, but one or two things you should know about the imaginary numbers is, because I said I is iota, which is under root of minus. So if you come across a calculation which says iota square, that means iota into iota. So when you do the square of this, the root goes, so what remains is minus. If you do iota cube means iota into iota square. Iota square is minus 1. So minus 1 into I, that is minus I. And iota raised to the power 4 will be square of this number, which is 1. So iota's 4 powers, if you know, the next power of iota is iota raised to power 5. That is going to be 1 into iota. Because 1 is already iota raised to power 4. So 1 into iota means iota itself. Then similarly, iota raised to power 6 will be whatever iota raised to power 2 was, that is minus 1. The same 4 numbers will appear again and again. So whatever power of iota, it can only be out of these 4 in the same order. I hope you got this. Now let's start distinguishing or distributing, classifying the real number. So as I said, the real number is the number which can be showed on number line. Real number, first of all, can be divided into 2 major categories. One is called as the rational number. Another is called as the irrational. Now, what are the basic definition of rational numbers and irrational numbers? Rational numbers are those which can be written in P by Q form, where P and Q belong to integer and Q cannot be basically 0. Q cannot be 0. If Q becomes 0, that becomes infinity. Infinity is not rational. So any number of this form. So if I say 2 by 3, is it rational or irrational? It is a rational number because it is already in P by Q form. 2 we can write as 2 upon 1. So that is also going to be P by Q form. That means rational. 1.3 we can write as 13 upon 10. So that means that also can be written in P by Q form. So all the numbers which are already integers or fractions or in decimal form, they all can considered as rational numbers. Of course, in negative numbers, it can also be counted. What about a number like 1.33333 up to infinity? Now, can you write this in P by Q form? So here, we knew that it is going to end eventually after 1 decimal. So we divide 13 by 1 and 1 0. Because after decimal, there is only 1 digit. So we divide by 1 and 1 0. But here we don't know how many digits are there. In fact, there are infinite digits. So can we write in P by Q form? Yes, we can still write in P by Q form. Basically, it is 4 by 3. Now, how it comes? We'll see that in a while. But all these numbers, which are called as NTR. NTR, it is not a name of a South Indian actor. It is non-terminating but recurring. That means the decimal, which does not terminate, but it recurs. If a same number is keep repeating like this, or same pattern, if keep repeating, those type of numbers, they are considered as non-terminating but recurring. And those also fall under the rational numbers. So all these type of numbers, they come under rational numbers. So what comes in under irrational then? Firstly, typically the surds come under irrational. Root 2, root 3. Root 2, root 3 are the numbers which can't be shown in P by Q form. You can't say root 2 by 1 because both have to be then integers. So those type of numbers which are surds. Surd means you are putting inside under root a number which is not a perfect square. Under root of 9 won't be irrational because under root of 9 is properly 3. But if I take cube root of 9, that will be irrational because 9 is not a perfect cube. So all such number which are surds, they are irrational numbers. Plus, you say NTNR. The numbers which are neither terminating non-recurring. For example, 1.3269835. So randomly, if you start writing anything and it is not ending at all, so those type of numbers, they will be considered as irrational. Now, what about the number which we call pi? Now, pi in mathematics or in calculation sake, we say pi is 3.14 or 22 by 7. Now, 22 by 7 is already p by q. 22 by 7, if I say, that will be rational number. But when we precisely say pi, pi is irrational number because the 22 by 7 is the approximated value of it. The actual value of it, it is anti-R, it is non-terminating, non-recurring number. If you have seen the movie Life of Pi, you must recall the scene where the hero writes the value of pi on the board and he keeps on going. The number is ever ending. So the actual value of pi is irrational. Okay, so you must take a note of it. Now comes the important part here, like numbers which are anti-R, if they are rational, how to convert those in p by q form. So for example, let's take the same example, 1.33333. If you have to convert that number into p by q form, let's consider this as a. Now after decimal, there is 1 3. We have to take that on our side. So what we do is we multiply this with 10. So both sides will have to multiply with 10. So the left hand side becomes 10a. The right hand side becomes, because you are multiplying it with 3, so the decimal point shifts by 1 unit to the right. So it becomes 13.33333. And then what we do is we subtract the original number from the new number. So on left hand side, we'll have 10a minus a, that is 9a. And on right hand side, we'll have 13.3333 up to infinite minus 1.33 up to infinite. So after decimal, there are 0.3333 up to infinite both sides. So nothing will remain after point once you subtract this. And on left hand side of the decimal, there will be 13 minus 1, that is 12. So a will be 12 upon 9. Dividing by 3 will get 4 upon 3. So as I said, the value of 1.33 is 4 by 3. This is how you can calculate. Let's take one more example. If I say the number is 1.434343, and if you have to convert that into p by q form, this time there are 2 digits after decimal which are repeating. So we'll have to get both of them on left hand side. So we'll have to multiply it with 100. So multiplying this with 100, we'll get 100a is equal to 143.4343 up to infinity. And then once we subtract, we'll have 100a minus a, that is 99a, is equal to 143 minus 1, that is 142. So a will be 142 upon 99. That will be the p by q form of the said number. Of course, there are short tricks and help people learn it this way. Like you just, if a number is this, so first on above, you write 143 minus the number which is not repeating, 1. So it becomes 142. And the number of digits repeat, those many 9s you have to write. So if 2 digits are kept repeating, those many 9s you have to write. But this short trick is not necessary, friends, as the original process is also not that difficult. That can lead you to unnecessary confusion. Plus, the topic is not so important for the exams. They may ask or may not ask the questions. So if you know the process, it should be fine. Easy. So take a note of these methods and do some practice based on it, because good questions can be, because they are process oriented questions. So challenging questions can also be formed, and our exams, they do ask different questions from different topics. There is no fixed pattern as such. So one must know these things about the conversion of NTR, non-terminating but recurring number, into its p by q form. Now, let's come to the next part of the bifurcation. That is how to convert now, how to divide now rational numbers into different parts. Rational numbers, as we know, are the numbers like 2, -2, numbers like 2.3, numbers like 1.3333 up to infinity. So, or in the fraction form, like 2 by 3. So all these type of numbers, they come under rational. So we can divide those numbers as integers, fractions, or decimals. And zero, basically zero we don't consider. Zero can be considered as integer. Sorry, zero can also come under integer. So integer will have -3, -2, 1, 0, 5. All these numbers they call as integers. Fractions and decimals. Now fractions are the numbers which can be written in P by Q form, or which are already written in P by Q form. Those kind of numbers are fractions. So 3 by 4, 5 by 11, all these will be fractions. And the decimals will be 1.3, 8.33333. All these will be decimals. Now, talking about the fraction, there can be subparts of the fractions. Proper fraction and improper fraction. Proper fraction means the fraction which is less than 1, like 3 by 4, 2 by 3. Improper fraction means the fraction which is greater than, equal to, or greater than 1. 4 by 3, 3 by 2. Because 3 by 2, we can write as 1 plus 1 by 2. 3 by 2, if you consider that fraction, can be written in mixed fraction form, like integer plus fraction. 1 by 2 will be the proper fraction. So that is why these are called as the improper fraction. These are called as the proper fraction. Now coming to the integers, integers further can be divided as negative and non-negative. The non-negative integers are also called as the whole numbers. Non-negative integers will have 0, 1, 2, 3. Negative will be, as you know, -3, -2, up to -1. Those will be negative integers. And non-negative integers, they are called as whole numbers. Whole numbers can also further be divided as 0. If you take out 0 from the whole numbers, what remains is 1, 2, 3. Those are called as positive integers or natural numbers. Because you use 1, 2, 3, 4 for counting, so they exist naturally. That is why they are called as the natural numbers. So this is how you can bifurcate as a natural numbers. Now further, these integers or natural numbers, they can be bifurcating in several types. The types can be now square number, non-square number. So you know what square numbers are, what non-square numbers. Cubic number, non-cubic number. Even number, odd number. Even number, odd number. Some of those will be even, some of those will be odd. You know the number if divisible by 2, they are even, not, then odd, and so on. But more important bifurcation for us is prime number and composite numbers. So the natural numbers, when divided as prime numbers and composite numbers, that is important for us. So what are all the prime numbers? Prime numbers are those which has exactly 2 factors. And composite numbers will be those who have more than 2 factors. So the numbers like 2 have only 2 factors, 1 and 2. 3 also has 2 factors, 1 and 3. 5, it has 2 factors, 1 and 5. So all these numbers, 2, 3, 5, 7, 11, they are prime numbers. Whereas the numbers like 9, which has 1, 3, and 9 as factors, 3 factors. 12, which has 1, 2, 3, 4, 6, 12. It has 6 factors. So all these numbers, 9, 12, 100, all these will be composite numbers. What about the number 1? 1 has only 1 factor. So it won't fit in any definition because it don't have exactly 2 factors. It cannot have more than 2 factors. So 1 is called neither prime nor composite. So 1 is called neither prime nor composite. One must remember that. That makes 2 as the smallest prime number. 2 is the only prime number which is even. 2 is only prime number which is even. You must know that part as well. Now, is there any identification of a prime number? That means a number, you see a number and can you decide by putting some formula that it is prime number or not? There is no such a method. Only method to be able to know the number is prime or not is to manually check dividing the number by the number smaller than that number itself and check whether any other number than itself and 1 divide it or not. For example, in case of 2, 2 is only divisible by 1 and 2 itself. That's why it is a prime number. 5 is only divided by 1 and 5 itself. That's why it is a. If any other number divides 5, then it would not have been then prime number. But nothing divides 5. That's why 5 is a. So there is only one universally accepted method to check whether the number is prime or not, is to manually try dividing the number smaller than the number itself and check whether any number divides it or not. But of course, we can ease that process a little bit, because for numbers like 101, you can't just try dividing it by 2, 3, 4, 5 up to 100. There is of course a way to do that, but formula wise we have nothing, and that is why people get Nobel Prize to find the biggest prime numbers. People get bigger prize. He found those many digits prime number. So it is a task that can only be achieved by computer or calculator. On some bigger scale, if somebody asks you whether the number is prime or not, you cannot answer. So nobody is going to even ask you. So that means you should know, or you must know, at least up to 100 all the prime numbers. So please Google it or manually start writing the list. So up to 50, you should know there are 15 prime numbers, and up to 100, there are 25 prime numbers. Okay, so please take a note, and take a notebook, a pen, pencil, and try jotting down all the numbers so that you don't miss any numbers, and keep revising those numbers once a while, because as I said, there is no another method to be able to know the number is prime or not rather than dividing the number smaller than. So you can't all the time do that. At least up to 100, you should know whether the number is prime or not. For example, 97. Is it prime or not? You should know that. Okay, because it is up to 100. Fine. But as I said, there is another method too. What you can do is, see, if I need to check whether the number, say 97, is prime or not. So what you have to do is, you have to calculate its approximate square root. Approximate square root means not to the even decimal point. It just up to 1 decimal point also you can. So 9 square is 81 and 10 square is 100. So this number lies between 81 and 100. So square root of this number should lie between 9 and 10. So you can just say 9. You can just say 9, approximately 9. So approximate square root, if you come to know that it is 9, then you have to keep checking the numbers, and not all numbers, only prime numbers. Prime numbers up to 9. So you just need to check whether the prime numbers up to 9, any of such number divide 97 or not. If not, then 97 is the prime. So what are the prime numbers up to 9? 2 is there, 3 is there, 5 is there, and 7 is there. Does 2 divide the number 97? No. We know now the D rule for 2. 2 does not divide 97. 3, for 3 we need to check sum of digits. Sum of digit is 16, so no. For 5, we know the last digit, so no. And for 7, you manually have to go. Manually you check whether this number divisible by 7 or not, so no. So because up to 9, no prime number divides this number, so now you can definitely say this number is a prime. This number is a prime. So this is the trick. You don't have to go all the numbers up to 97. You just have to go all the prime numbers up to its square root. Okay. So now let's take one more example. If I need to check 117 is prime or not. 117 is a number which is prime or not. So approximate square root will be 10. because 11 square is 121. It goes beyond that. So up to 10, you just need to check all prime numbers. So 2, 3, 5, 7, only these 4 numbers we need to check with. 2 does not divide this number. 3 divides this. So because 3 divides the number, it cannot be a prime number. Got this? So it is not a prime. It is composite number. So this is how you are going to decide whether the given number is prime or not. Okay. Now let's see the next part of it. That is the base system. Now, in our exam, especially EPFO exam, if you're targeting, they have asked a question in one of the year that convert this into decimal system. This is the number which is in binary, I think 3 ones were there, 10110 into the decimal system. So now the question is very easy, very doable. If you have done the computer as a subject already, you can solve it very, very easily. But for those who never have heard the word like binary or decimal, they can find this question really tricky. So that's why we'll see only basic part, not too much into the depth, because conversion is very easy. So let's consider this. See, the system that we follow or our mathematics, we all do all the calculation or we use for counting, the system that we use is called as the decimal system. Take mean 10. So our base is 10. Base is 10 means what? We use 10 symbols to write our number. The symbols that we use is 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. These 10 symbols we use. So if you need to now go beyond 9, the next number 10, which is consist of the same 2 symbols we already have written, 1 and 0. The 10 is consist of 1 and 0. Then 11 will be 1, 1. 12 will be 1, 2. So same symbols now we will be using to write down the upcoming numbers after 9. So that means we have only 10 symbols to write our number for. That's why our system is called decimal system, that is base 10. But the system that the computer uses is called as the binary system. A binary means what? The base is going to be 2. So computer understands only 2 symbols, that is 0 and 1. So binary has only 2 digits or 2 symbols, 0 and 1. So all the numbers consisted in binary will be used using only 0 and 1. Okay, so what is the first number of our decimal system? If we talk about that is 0. So 0 has only 0 into it. So binary's first symbol or first number is also 0. In decimal system, the second number is 1. 1 has only 1 into it. So binary also can use 1. So binary is also second number is 1. So that means the conversion, if you do 0 in decimal will mean 0 in binary. 1 in decimal will mean 1 in binary. But when you say 2 in decimal, now binary does not have 2. Binary will have to use the same digits again. So after 1, which is the number in our system, which consists only 1s and 0, it is 10. After 1, it comes 10. So that means 2 in decimal, it means 10 in binary. Next number is 3. So which is the number after 10, which uses only 1s and 0s. After 10, it comes 11. It uses both 1. So 3 in decimal means 11 in binary. Next number is 4. 4 in decimal, which is the number after 11, which consists of only 1s and 0s. It directly now goes to 100, because 12, 13, 14, all the number will have different symbols than 1 and 0. So directly we'll have to use 100. So 4 in decimal means 100 in binary, and so on. This is different conversions we can use. So if I ask you, convert 7 into binary, convert the number 7 into binary. So what is the way to do that? It has a very unique way. What you do is, you divide that number 7 with 2, because you have to convert in binary. And then you write the quotient here. So 2 3s are 6. The complete quotient is 3. and remainder is 1. So remainder you have to write it here. Remainder you have to write it here. Then whatever the quotient is, you again have to divide it with 2. 2 ones are 2. So 2 goes out of 3. What remains is 1. Now you can't divide this 2 because this 1 is already lesser than 2. So once you achieve at this point where this number is already smaller than our base, so we have reached our conclusion. You just have to make sure that you write in reverse form like this. You write in this order. 1, 1, 1. So 1, 1, 1 will be the binary code for 7. Will be the binary code for 7. We can continue this list and check quickly. For example, 5 will be the next number is 101. 6, the number after 101 is 110. And 7, the number after 110 is 111. So yes, 7 has 111 code. Let's check for 9. If you need to check for 9, what is the binary code for 9? So divide 9 by 2. The complete quotient is 4. The remainder is 1. Divide 4 by 2. The complete quotient is 2. The remainder is 0. Divide this 2 by 2. The complete quotient is 1 and the remainder is 0. And then you write in this order. It becomes 1001. So yes, 8 will be after 111, it comes 1000. And for 9, we'll have 1001. Now let's check quickly as a revision for 8 as well. For 8 as well. So 8, if you try to divide it with 2, it goes 4 times, the remainder will be 0. 2 when you divide 4 times, quotient will be 2, the remainder will be 0. 2 when you divide with 2, the quotient will be 1 and the remainder will be 0. Once the quotient is 1, you have to write in this form from here to here. So 1000 is the code for 8, as you can see it here. 1000 is code for 8. So this is how you convert a decimal number into the binary. But what if you have to do vice versa? If you have to do vice versa, for example, a number is 1001. And this time, let's take another example. If you have to divide, let's say 1010 into the binary. This is into binary. If you have to convert this into the base 10. So this process is exactly like the process we use in our school days to write a place value form. Place value form. For example, if I write the number 432 in its place value form. So how do you write? 4 is on a hundreds place, so we write 400. Plus 3 is on a tens place, so we write 30, 3 into 10. And 2 is on a unit place, so we write 2. So what basically we do is, because 4 is at the hundreds place, so we multiply 4 with 100. 3 is at the tens place, so you multiply 3 with 10. And 2 is at the unit place, so you multiply 2 with 1. Our system is decimal system. So that's why the numbers that we are multiplying, they are in tens power. So this is 10 raised to the power 2 plus 3 into 10 raised to the power 1 plus 2 into 10 raised to the power 0. So basically, we multiply with tens increasing power from rightmost side numbers. From rightmost side numbers with tens increasing power. First power is 0, then 1, then 2. So same way we have to do here. This 1, 0, 1, 0. We have to multiply this with increasing power, but because the base is 2, so we'll multiply with increasing powers of 2. So multiply here with 2 raised to the power 0. This one, we multiply with 2 raised to the power 1. This 0, you multiply with 2 raised to the power 2. And this one, you multiply with 2 raised to the power 3. And then you add that all. Like we did it here. 2 raised to the power 3 into 1 is 8. Plus, this is going to be 0 because you're multiplying with 0. Plus, 2 raised to the power 1 means 2. Plus, this is again 0. So 8 plus 2, that is 10. So yes, the decimal converted form for this number is 10. Okay. Now let's see for some another scale. For example, 11010, if you have to convert from binary to decimal. So as I said, what you have to do is you have to start multiplying the last number with 2's increasing power. So 0 into 2 raised to power 0. This 1 into 2 raised to power 1. This 0 into 2 raised to the power 2. This 1 into 2 raised to the power 3. And lastly, this 1 into 2 raised to power 4. And just add this one. This will be 2 raised to power 4 means 16. Plus 2 raised to power 3 means 8. Plus that will be 0. Plus this will be 2. And this will be again 0. 16 plus 8 plus 2 means 16 plus 8 plus 0 plus 2. That is 26. So here, the converted form into decimal is going to be 26. So this is how you can convert from one base system into the another. So this is about the base system 2. But what if the base system is 3? So base system is 3, called it's a tertiary system. It will have base 3. So base 3 will use the symbols like 0, 1, and 2. It will use 3 symbols, 0, 1, 2, up to 2. Base 3. Base 4 can also be there, which uses the symbols 0, 1, 2, and 3. Similarly, base 9 can also be there, which uses 8 symbols, 0, 1, 2, 3, 4, 5, 6, 7, 8. Which uses 9 symbol up to 8. What if the system is there which has more digits than ours? Base 12 can also be there. Base 12. No decimal. So base 12 will have 12 symbols up to 11, but 11 is not a symbol. 11 is already consist of 2 basic symbol, 1 and 1. So you write 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. 10 symbols are done. The next symbol after this, we use symbol. We can't write 10. 10 is already consist of 1 and 0. So the next symbol we use is A. And for 11, for last symbol, we use B. So A is like the 10. A can be considered as 10 and B can be considered as 11. And so on. So you can form your own system. There can be base 16, hexadecimal system, dodecadecimal system like this one. So if the base is 16, there will be 16 symbols. So after 9, you have to use as 10, you have to use A. For 11, you have to use B. For 12, you have to use C. For 13, you have to use D. For 14, you have to use E. And for 15, you have to use F. So up to F, the hexadecimal system will have symbols up to F. Okay. And how to convert from one system to another? Same thing. Let's take one more example. If you have to convert a number, say A12, which is in base 12, we have to convert that into base 10. So base 12, if you have to convert into base 10, so you know the process. You have to take the last digit and start multiplying with the increasing powers of 12. So take this 2, multiply it with 10 raised to power 0. Take this one, multiply it with 12 raised to power 1. And A means what? 10. A is like 10. Take the 10 and multiply it with 12 raised to the power 2 and just add this one. So it will be like 12 square into 10, 1440, plus 12 into 1 is 12, plus 12 raised to the power 0 is 1, 1 into 2 is 2. So it is like 1454, 1454 in base 10. And if you have to go vice versa from base 10 to another base, let's say a number in base 10 is 85 in base 10. If you have to see what is the number in base, say 9, base 9, then you divide it. Then you divide 85 with 9 and check for the quotients and the remainders. 9 nines are 81, remainder is 4. Then again you divide 9 by 9. 9 ones are 9. The remainder will be 0. So then you can write 104. So 104 in base 9 means 85 in base 10. Of course, very rarely they have asked the question. So it doesn't make sense on doing practice for much practice for these type of questions. It is just about knowing the stuff, how it is to be done. And if you do sufficient practice, 5-6 examples on your own, then you can solve it in any exam if they ask, right? So restrict your practice for smaller numbers first of all. They are never going to ask bigger numbers because these exams are not calculation oriented exam. They don't provide you the calculator. So they can't be asking you a huge number and convert it into some base. Nobody is going to do that, right? So restrict your practice to the smaller numbers and on smaller scale as well. Don't do much practice. 10 odd question, it should be sufficient. Now let's do the last topic of this session that is important for us, which we call unit digit cyclicity. Now, what do you mean by unit digit cyclicity, or what kind of questions they ask based on unit digit cyclicity? A question could be, what is the unit digit of 2 raised to the power 8? Now, 2 raised to the power 8 means 2 into 2, 8 times, 2 into 2 into 2, 8 times. So you can go manually also. It's very easy. 2 into 2 into 2, 8 times. It's 256. So last digit is going to be 6. But if it is on a bigger scale, 2 raised to the power 18 is asked, 2 raised to the power 118 is asked, then what to be done? That is what we are going to learn in this session. So consider 2 raised to the power 19 if you want to find the last digit for 2 raised to the power 19. So for that, you'll have to observe how the cycle of 2 is formed. That means if I put n is equal to 2, so how the cycle of 2 is going to go? For n raised to the power 1, n raised to the power 2, n raised to the power 3, n raised to the power 4, n raised to the power 5, n raised to the power 6, n raised to the power 7, n raised to the power 8, n raised to the power 9, n raised to the power 10, and so on. So if you put n is equal to 2, 2 raised to the power 1 is 2. 2 raised to the power 2 is 4. That means 2 into 2, 4. 2 raised to the power 3 means 4 into 2, that is 8. 2 raised to the power 4 is 8 into 2, that is 16. But we are just concerned with unit digit. That means the last digit. So I'm only writing 6 here. 16, 6. Because in any product, the last digit is decided by the last digit only. For example, if I ask you 23 into 26, what is the last digit? So you can just do 3 into 6, 8. Last digit is 8. 18 is 8. So last digit is decided by the last digit. Hence, we are only writing the last digits. 6 into 2 is 32 is 2. 2 into 2 is 4. 4 into 2 is 8. 8 into 2 is 16, 6. 6 into 2 is 12, 2. 2 into 2 is 4. So if you observe, 2's whatever power, it can only end with 2, 4, 8, 6, 2, 4, 8, 6, and in this same order. 2, 4, 8, 6, 2, 4, 8, 6. These 4 numbers are going to appear again and again and again in the same order. So if you, let's say, want 2 raised to the power 7, so you can say 2 raised to the power 1, 2 raised to the power 2, 2 raised to the power 3, 2 raised to the power 4, 2 raised to the power 5, 2 raised to the power 6, 2 raised to the power 7. So whatever the 2 raised to the power 3 had will be 2 raised to the power 7's last digit. And as you can see, it has last digit as 8, which 2 raised to the power 3 also has, because the same 4 numbers appear again and again and again. So because the 4 numbers appear again and again and again, we call the cyclicity of 2 is 4. So what we do is, we take this 7, we divide it by 4, and we check the remainder. And the remainder is 3. That means out of the batch of 7, first 4 if you remove, what remains is 3. 1, 2, 3. So whatever the power of 3, whatever the power 3 of 2 will be the power 7. So you take this 3 and you raise as the power of 2. And 2 raised to the power 3, as we know, is 8. Or it ends with 8. 2 raised to the power 7 will also end in 8. So I hope you got what to do now. If you have to do 2 raised to the power 19, take this 19, divide it by 4, because the cyclicity is 4. Check the remainder. Remainder is again going to be 3, because 16 goes, what remains is 3. Then raise the 2's power as this 3. And the last digit is going to be 8. If I want to do 2 raised to the power 21, so take 21, divide it with 4, check the remainder. Remainder is 1. So raise 2's power 1. So last digit will be 1. If a bigger number is asked, 2 raised to power 1286. So you don't have to divide the entire 1286 with 4, because we have seen the divisibility rule for 4. And we know divisibility rules can be used to find the remainders. So what you can do is, because we have to divide the entire number by 4, we just divide last 2 digits by 4, because divisibility rule of 4 is last 2 digits. So you just take this 86, divide it by 4, check the remainder. Remainder will be 2, because 84 goes, what extra is 2. And then raise this as 2's power. Raise this 2 as 2's power. Last digit is going to be 4. Okay. What if you have to do 12 raised to the power 26? Then again, it does not matter what it is in front of 2. Because if 2 square is 4, 12 square is 144. The last digit is decided by the 2 only. So last digit will be decided by the 2 only. So you don't have to consider whatever written in front of 2. You just take this 26, divide it by 4, check the remainder. Remainder will be 2 again, and raise this 2 as 2's power. So last digit will be 4. And one more last thing. What if the number is divisible by 4? For example, 2 raised to power 24. What is the last digit of 2 raised to power 24? So if you take 24, divide it by 4, and check the remainder, remainder will be 0. So you can't say now 2 raised to the power 0, that is 1 is the last digit, because 1 can't be last digit of any 2's power. So remainder if coming 0, you can't raise the power as 0, because 0 power is not there in the cyclicity. Cyclicity start with power 1. So power can be either 1 or 2 or 3 or 4. 5 means again 1, 6 means against 2, 7 means against 3, 8 means against 4. So if power is 0, you have to consider the power as 4. So if remainder is coming out to be 0, you have to take remainder as 4, and you will raise 4th power of 2, which ends in 6. So the last digit here is going to be 6. The last digit here is going to be 6. Okay. Now one can get puzzled that this is everything is just for 2. What about 3? What about 4? Don't worry. 4 is the universal cyclicity. Universal cyclicity. The cyclicity 4 can be applicable to all the digits. For that, we need to form a table. So let's quickly form a table. What we are going to do now is, we are going to put the different values of n. And then we are going to calculate n raised to power 1, n raised to power 2, n raised to power 3, n raised to power 4, n raised to power 5, n raised to power 6, n raised to power 7, n raised to power 8, n raised to power 9, n raised to power 10 for different values of n. So if you put n is equal to 2, so 2 raised to power 1 is 2, 2 raised to power 2 is 4, 2 raised to power 3 is 8. And we already seen this. 8 into 2 is 6, 6 into 2 is 12, 2, 2 into 2 is 4, 4 into 2 is 8, 8 into 2 is 16, 6, 6 into 2 is 2, 2 into 2 is 4. So 2 cyclicity as we know is 4. Then comes the 3. 3 raised to power 1 is 3, 3 into 3 is 9, 9 into 3 is 27, 7, 7 into 3 is 21, 1. That means 3 raised to the power 4 will end in 1. So now if you do 3 raised to the power 5, that means 1 into 3 when you do, it will again become 3. 3 into 3 again will become 9. 9 into 3, 27, 7. 7 into 3, 21, 1. 1 into 3 is 3. 3 into 3 is 9. So here you can observe same 4 numbers, 3971, 397 will again appear. That means the cyclicity here also is 4. So whatever we learned for 2, same thing can be applied if the last digit is 3. Then comes the 4. So for 4, 4 raised to power 1 is 4. 4 raised to power 2 is 6. 4 into 4 is 16, 6. 6 into 4 is 4. 4 into 4 is 6. 6 into 4 is 4. 4 into 4 is 6. So 4, 6, 4, 6, 4, 6. They'll keep appearing. So in case of 4, it is in fact more easy to calculate any power if I ask you what is 4 raised to power 16. So you know, 4's odd power, last digit is 4. 4's even power, last digit is 6. Odd power 4, even power 6. So if it is an even power, the last digit is going to be 6. So no need to even go for the rule of 4 or division by 4 or use the cyclicity in case of 4, as even and odd power only decide what is the last digit. Then comes the 5. 5 raised to power 1 is 5. 5 into 5 is 25 is 5. 5 into 5 is 25 is 5. So everywhere it is going to stay 5. So 5 is even simpler than 4 because 5 is whatever power will always give only 5. 5 raised to power 89, if I ask you, what is the last digit? It is going to be 5. Same is stuff with 6. 6 raised to power 1 is 6. 6 into 6 is 36 is 6. 6 into 6 is 36 is 6. So everywhere it is going to stay 6, 6, 6, 6, 6 everywhere. So the last digit is going to stay 6 throughout. Then comes the 7. 7 raised to power 1 is 7. 7 raised to power 2 is 49 is 9. 9 into 7 is 63 is 3. 3 into 7 is 21 is 1. 1 into 7 is 7. 7 into 7 is 9. 9 into 7 is 63 is 3. 3 into 7 is 1. 1 into 7 is 7. 7 into 7 is 9. And so. So for 7 also, you will have to apply the rule of 4 as the cyclicity is 4. Then comes the 8. 8 into 8 is 64 is 4. 4 into 8 is 32 is 2. 2 into 8 is 16 6. 6 into 8 is 48 is 8. 8 into 8 is 64 is 4. So 8, 4, 2, 6, 8, 4, 2, 6, 8, 4, 2, 6. Same 4 numbers will keep appearing. So here also you'll have to use the cyclicity 4. And lastly comes the 9. 9 raised to power 1 is 9. 9 into 9 is 81 is 1. 1 into 9 is 9. 9 into 9 is 81 is 1. So 9, 1, 9, 1, 9, 1, 9, 1, 9, 1. They will keep appearing again. What about 0? 0 will give 0 at the end digit anyway. And 1 will also give only 1 as the end digit. So for 1 and 0, you don't have to think even. You just think about these numbers. So here are 3 types of numbers. The numbers I have written in white, that is 2, 3, 7, and 8. For here, you will have to use the cyclicity 4. Here you will have to divide the power by 4 and check the remainder and raise the remainder as the power to find the last digit that we have seen. Then there are the numbers which I have written in blue. Those are 4 and 9. Those goes as odd, even, odd, even. Odd power 9, even power 1. Odd power 9, even power 1. And here 4, 6, 4, 6. So in case of 4 and 9, you have to check odd powers or even powers. And the numbers I have written in yellow, which are 5 and 6. They will always be 5 and 6 throughout. 5 will end in 5, 6 will end in 6. Okay.